Our next speaker is invited also is Suman Datta. He's from Penn State. He spent 8 years at Intel, the Advanced Transistor Group, and has been at Penn State since then, just now recently joining Notre Dame.
Right. Thank you, Alan. Thank you, Eli, for inviting me. I got a momentary scare because I was also supposed to be at Sonic Review at Illinois. And then when I realized that this is Friday and not Thursday, I'm like, wow. OK, because I'm not a quantum matter yet. So I'm going to talk about a little bit about, I don't know whether to call it an optimistic or a pessimistic talk, but more I would call it a realistic presentation of where we are, what have people built, what we have built in our group in terms of interband tunnel transistors, and some analysis I'm going to present on that. And based on that, I'll let you be the judge whether we should call it quits or whether we should continue to work on this device, emerging device. So simple stuff. The promise of tunnel FETs. I think we heard about that. So I'll just emphasize that. Why tunnel FETs? Straight go into the experiments. We build the devices. We characterize them ourselves. So we have a certain level of confidence in that. But most importantly, after that, I'll also try to benchmark with what other folks have built around the world. And you will see that there is a certain pattern, if you will, that's emerging, consistent with what we heard today. And from that, I think much remains to be done. And are we working on the right material systems? It was very intriguing to hear about this OJ generation process. I have to think a little bit more about that. But clearly, there are some fundamental challenges on our way. So, why the reason for stiff switching FET? The whole idea is voltage reduction and energy efficiency. And if you have a MOSFET, state of the art, then the goal is that we'll never be able to compete with ion, especially as we go to any reasonable overdrive. But this tunnel FET, in my opinion, is something that is competing with subthreshold CMOS. Now, whether that's a strong value proposition or not, let the industry decide. But that's where what we think is our, and already we have work cut out for us to try to do that. Okay. So the promise of this tunnel FET is fundamentally based on, as we heard today, is sub-KT over Q operation. So if we can't do that, and we cannot do that, then we are in bad shape. And if we cannot build up any reasonable amount of current also, by the time we come out of that sub-KT over Q operation, then we are also in a bad situation. So those are the two things that we have to balance and see whether we can get there. So I think I'm going to skip that because you already are familiar with this talk. The main thing is that the tunneling by itself is not a sub-KT over Q. In fact, when you have a lot of tunneling, when you separate out the bands, tunneling doesn't really change much in terms of voltage or in terms of you're just changing the density of states in that case. But basically, the reason why tunnel FETs has received so much attention for sub-KT over Q is the action is going on right when the bands are separating. That's where most of the action is in terms of sub-KT over Q. And then you have to very quickly get up to the point and reduce this barrier height and width. And height is one of those things that comes from band gap engineering in order to get that right on current. Okay. So we looked at state of the art, meaning good conferences, VLSI, IEDM, good journals, where people have made different types of devices, and this is on current versus minimum switching slope. If I'm missing someone's device, it's purely unintentional. The basic point I'm trying to make is that that if you draw this 60 millivolt per line, and you want to stay somewhere over here, and this is already, I'm picking probably the minimum switching slope. This is the best case scenario. Even minimum switching slope is a question mark because you're looking at you should be looking at an average switching slope over a certain voltage rate. So even then, you can see, yes, there are some demonstrations, particularly in the silicon-based systems, but the problem is that the on-current are extremely low. Okay, you get some advantages by going to strained silicon nanowire in terms of boosting the on-current. If you're careful with, there's a normalization issue and so on and so forth. But still, you can see that the story on the p-channel tunnel FET is not that promising in that sense. So we have a problem. Now, people have done some work on trying to get to some band gap engineered systems by trying to introduce germanium And more recently, people are trying to also look at germanium-10-based systems. But there are significant material challenges as well as dielectric issues, doping issues that you have to overcome to try to get up and go to the left. Okay, so that's one issue. I'm going to skip this thing for sake of time. And let's revisit the N-channel, because ultimately this is digital technology. You need to get both going. And in N-channel tunnel FET, turns out there are a lot more data points. And again, silicon system, there has been some pretty impressive demonstration in terms of minimum switching slope, but they're at very, very low. Again, by the time you try to get, drive these transistors, there's not much of current that's coming through. So on the other hand, folks have, including our group, we've worked quite extensively on these 3-5-based systems. Then the real advantage is that the materials growth is fairly in place, both in the arsenide system as well as even mixed arsenide antimonide system, thanks to the photodetector community. And so the material was reasonably mature that you can go and build devices. But every time you try to go in that direction of improving on current, yes, you get on current, but you also start degrading the switching slope. So that's kind of the situation. So we are still kind of missing any real data point in the space where we really need to go to. Okay, this is starting to sound more pessimistic. So anyway, let me tell you a little bit more about the N and the P channel tunnel FETs that we recently demonstrated. The way we were, projecting this thing at, okay, these are all sharing the same metamorphic buffer. Eventually, of course, you have to do all these things on silicon. So there's the next level of challenge. Okay, but if you can come up with a system that gives you both good end performance and good peak performance, that this is something that's really worthwhile taking a look at. The reason why we picked these material system is that it gives us an opportunity to do bandgap engineering on both sides, both on the p-channel side when you're tunneling from this conduction band, or you can talk about the holes coming in, tunneling through, or the valence band electrons tunneling out. And 0.31 EV, 0.25 EV, they're reasonable. They're right at the ballpark where you need to be be competitive with silicon FinFET. But anything below that would be even better. But then if you go too low, then we're going to end up with some of these generation recombination, Auger type of issue going forward. So the other advantages of these material systems is that they can be grown by emissivity and MBE, and so reasonably high quality. Now how high? These are all qualitative statements. You have to quantify these things, but these days people, thanks to all the advancements in microscopy, we can actually go and do tomography to actually see how these atoms are and what kind of abruptness that you can really get at these junctions. In fact, we have an IDM paper upcoming on these kind of characterizations. So if you try now taking that material system, we build obviously devices, and I'll show you the IV data, but we also do calibration, and because we have the band-to-band tunneling current, some of the interface state densities, trap-assisted tunneling, and so on and so forth. So if you do that, this is what we think is probably achievable. So based on that, I did not take the TSMC FinFET, but I took something similar, the 22 nanometer Intel silicon FinFET. Maybe my past connection, that's the reason. And then you see that this is one option that if you match the off current, yes, you can get some advantage right at that particular point of time. But as soon as you go below like 0.4 volt or so, and this is the best nominal device, right? And in this material system, okay, you go to then you go crossover, and you're not really. On top of that, there are other nuances of HTFET, which is this Miller capacitance effect because of the asymmetry between source and drain. So when you actually do inverter simulations, you have to take those into account as well. So when you go and take a look at this is an inverter simulation only. Then you see that energy per cycle versus delay. Okay, this is your silicon 22 nanometer FinFET. Already for 40 nanometer, I'm hoping that there is another line that's already in commercial production. So now you're looking at, now we have to do this entire design at a smaller LG. This was done for 22 nanometer. You can see that till about 0.4, even then, because of that enhanced Miller cap effect, even though you see a gain, but it's not translating to any circuit level advantage. So you've got to go even further down. So now you're really competing with subthreshold CMOS. So that's why it goes back to my original statement, that that's the space, at least where we see where these kind of tunnel FETs would be interesting. All right, now let's come back to building this device and showing whether we can even get there. And this is I mean, I've spent a large part of my career building logic MOSFETs, but this turns out to be, you've got to get everything right that you've got to get right in a MOSFET, plus a few other things you have to get it right. That's what makes this device so challenging. And it's all starts with, you got to get all the electrostatics right. So in order to get all the electrostatics right, you got to make a multi-gate, thin body, and ultra-thin geometry, very thin TOX. All those things have to be there, first in place. So if someone is claiming, sub 60 millivolt per decade, but you see a gate oxide that's like 3 nanometer, you start asking questions, how is that even possible, right? So those things have to come together. Now, gate length, of course, in research devices, we can study long gate length devices, 100, 200 nanometer. Then the next question is abrupt tunneling junction. It has to be abrupt. It has to be very high quality as well. Otherwise, things like Shockley-Reed-Hall, as Uyghur was mentioning, will be an issue, right? So you've got to get very nice quality junctions, heterojunctions, compositionally different, as well as you're also switching the doping. Whether your doping is going to line up with your compositional metallurgical junction, that's also the question, and that can also affect these characteristics. On top of that, and this is where we spend a lot of time last 5-6 years, is this interface, because if you have those interface states in between that in that band gap, that forbidden gap, which is essentially what you're relying on to filter out the high energy states, then that trapezoid-Stirling and thermionic emission is going to ruin the party. Okay? There are other smaller design issues for lower band gap, but they go away if you restrict your drain voltages, and since we are interested in subthreshold, that's not an issue. So anyway, we start off, this is just to quickly give you an idea how we build this device, because I'll go back and say that these non-idealities can come from not only just the materials related issue, but also from fabrication related problems. So we make this kind of vertical structure very similar to the MIT device that was shown earlier today. And you form this mesa pillar. You try to make a very narrow pillar as possible, and then you have to passivate it, and then you got to put your gate down. So if you want to make a very narrow, thin body, then you have to turn on the physical component of your edge. Now you're hammering on that sidewall. If you turn on more the chemical component of your edge, then you get a very, very tapered profile. So yes, so you have to treat this thing very carefully to see how you can preserve this high quality surface. And this is really a challenging problem. I never say never, but that's something. But then you can go ahead and make these devices and characterize these devices. In fact, we can have great ground signal ground. We can even do high frequency measurement. We did this pulsed IV that David just talked about with the NIST guys with high gain bandwidth systems. So these are the kind of representative structures. They're not quite ultra thin body, and that is something I have a student working on that. They're about 100 nanometer, maybe 120 nanometer or so, all said and done. And these are the P-channel tunnel FET. These were N-channel tunnel FETs. Okay. Quick thing on interface states. I don't want it becoming a big lecture, but the problem is that in P-channel tunnel FET, when you do the bandgap engineering, you're trying to make this device work on a channel material, which is gallium arsenide and antimonide. Okay. When you're trying to do it on N-channel, you're trying to do that on indium gallium arsenide. Okay, so you have to re-optimize this high K on completely two different channel materials. Okay, so that's another issue. Antimonides is a pretty interesting test case. This dark current in photodetector community, they have been bothered by this thing quite a bit. And I think maybe if we don't succeed in building a tunnel FETs, maybe we can help them finding a better passivation, because we have been able to, over the last 3 years, been able to get a lot of progress on trying to get a high quality passivation, and I believe that Professor Takagi is also working on some of these issues of how to control, get a good CV characteristics. For antimonide, it used to be almost flat, but now you can see that you can get very nice CV modulation. There's still a bump, mid-gap DIT right there, and you still get interface states coming up as you approach the valence band. Okay, so these things are all going to come back. We have done similar optimization on NT-FET, and this work was motivated by the work that Susanna Stemmer's group was doing at UC Santa Barbara, and we were inspired by that, and we can get reasonably good a dielectric interface on using zirconium oxide in gas. But again, you can see these little bumps in the CV, and you can see that in the conductance spectrum as well, which tells you that there's still these states sitting right in the middle of the in-gas band gap. So a lot of progress, but not quite there yet. So this is PT FET, this is NT FET, and that's where we are. Okay. So based on that, we can make devices and ID versus VG characteristics, and I'm showing the DC, all room temperature, and then different pulses, pulsed IV characteristics. And when you do that, you say that for P-channel case, yeah, we start with a pretty horrible subthreshold slope, and then we start improving it. There are all these features that are still showing that there are all these DITs that are with different peaks that are showing up in this band gap, and we are far from that 60 millivolt per decade. But this is one of the first demonstrations of P-channel tunnel FET in this mixed arsenide and antimonide systems. On the N-channel tunnel FET, things were better because the dielectric interface was better. It's a more mature system. The in-gas system, I think the antimonide, as far as channel and antimonide interface is concerned, it's still quite a new story. And when you do that, again, as was being pointed out by the previous speakers, yes, we get that switching slope versus drain current. But again, it just kisses that 60 millivolt per decade and then takes off again. Okay, so there is some kind of commonality in all the data sets that. But of course, to get this paper published in VLSI, we had to claim, of course, right there, 55 millivolt per decade at room temperature. But anyway, but you get the message. Okay. The other interesting thing is that all our devices that we have built, including N-channel, P-channel, they're indeed tunnel FETs. The reason why I say that people sometimes confuse parasitic MOSFET with a tunnel FET, and the reason not to do that would be to look at the entire output characteristics, both the forward as well as the reverse, and you should see this a nice Isaki diode, which is sort of built into your tunnel FET, right? So we did that. We see the very pronounced at room temperature. Of course, it gets even better at 77 Kelvin. But on the drain current side, on the P-channel side, you see we kind of try to see that. We don't see that at 300 Kelvin, and that's because of, I think, the states are still pretty high. But as soon as you cool it down to 77 Kelvin, you get it right away. Okay, so here we go. In fact, while I was flying over, there was this email that was going around, which is this recent work that just came out in The Nature, which is this 2D material systems of germanium and MOS2. There was very nice claims of sub 60 over 1, 2, 3, 4 orders of magnitude. It's very impressive work. It's not clear yet. I think the community will debate on exactly how that is coming along. But it's more like an in-plane or line tunneling type of a device. But I think the first thing is that, yes, we have seen this story before with silicon nanowire. We have seen this with larger bandgap system. This is also a larger bandgap system, particularly MOS2. So yes, you see that. But again, I think our problem is trying to get to somewhere in this space in terms of drive current. And over there, we are still in this situation where we are still kind of stuck with that 55 millivolt per decade. So I'll just end the talk saying that, yes, we actually quite a while back, when I first got into this tunnel FET business at Penn State, one of my first PhD was looking into this measurement, and we did temperature-dependent IV characteristics and try to figure out whether there is, which part is band-to-band tunneling. So I call it components of transport in tunnel FET. Which part is this trap-assisted tunneling, and then, as Igor was pointing out, there is this floor that you just can't go beyond, which is related to Shockley-Reed-Hall type of a generation rate. And only way you can kill this thing is, of course, go to larger band gap, and I think that's why some of these people might have seen this sub 60 millivolt per decade, because that's where the bands are separating. But in the narrow gap systems, you really have no other way but to make sure that it's very thin. So if you do that, then you can break it down into what would it entail to actually see that sub 60 branch. Yes, it has to come from pure band-to-band tunneling, but unfortunately, Mother Nature doesn't behave that way, and we have to deal with other components. The question is, how much can we lower this thing so that eventually we can still escape that? Okay, thank you very much.
We'll have time for one question.
So, I mean, this is a question I'm going to ask during the discussion period, but I might as well introduce it. A lot of discussion about subthreshold slope. All of the last two slides you had subthreshold slope on the right-hand side. And here's another one. And the issue that was brought up earlier this morning by Patrick Zhao had to do with the a curious dimensionless ratio. Well, I'm a big fan of dimensional analysis. And so, wait a minute, I have a 2D density of states of 10 to the 12 and a trap density of 10 to the 11. There's a dimensionless ratio that tells you that the on-off ratio is going to be bad. So it's not the subthreshold slope. It should really be the on-off ratio.
It should be on-off ratio, yes. And I think...
And it doesn't appear here.
Well, it is sort of built in here. You can probably try to get that. If I put a MOSFET curve on that, you can start seeing that right away. But I see your point. I think the main thing that I'm trying to mentally go through from just density of states argument, the units are still, there's an EV in one case, the other.
No, they both have units of EV.
Per centimeter square per EV.
It's exactly the same
It's
units.
exact. Okay. So then the question comes back to, is there any other thing in the prefactor in terms of the dynamics? I think that's the only thing that we can play with. The tunneling versus the trap response time.
Yeah, there's not much leverage on the prefactor. So, and this applies to Professor Esseni's discussion as well, is that a lot of discussion about subthreshold slope, and unfortunately the problem seems to be the on-off ratio is in real trouble.
Oh yeah, it's that's why I think you got to start looking at this axis very carefully. Yeah.
Okay, let's thank our speaker one more time.